So actually, I had stopped at this point that difference between forward and backward chaining. So in that thing, the proper what is the symbols did not get printed. So let me just highlight here and just explain. So see here, forward chain is nothing but if suppose you have the data will be there and you have to prove something to reach to a conclusion. So what you will do, you don't know the goal over here, but you will collect data. Okay, starts with the known fact. Okay, if you read, you should start with the known facts and applies inference rules to extract more data until a goal is achieved. So you will be collecting data which will lead to the goal. But in backward chaining, you will be knowing the goal. So to what is reaching the goal, backwardly you will be proving those steps. Okay, starts with the goal node and works backward to determine what fact must be due to achieve it. True must be true to achieve it. Okay, so this you can simply say data driven, this you can say goal driven, and then you can say process starts with initial facts, apply rules to generate new facts, then continues until the goal is found. Here starts with goal node. Okay, find rules that concludes the goal, then recursively prove the premises of those rules until known fact. Premises means suppose this is the goal. Okay, these two things are there. In these two things, they will have their own premises like this. Okay, so here this we will be doing, then we'll prove this. We know this. Then how we got this? We'll say with this two. Then we'll prove this premises. Then we'll go to the first thing. Okay, understood? Like that it is. Okay, until the known fact are found. Okay, which should be proved. This are found. Then use for cases. So it is suitable for the situation where all facts are known and the goal is unknown. So you know the all facts are there. Suppose some facts only P implies Q is there. Okay, but what's the result you don't know. You know what we are doing, but you don't know the result. So in this case, which means you know the initial all the data is given, but the goal is unknown. But here, suitable for the situation where a specific goal is known. Okay, goal is known, and you need to derive if it can be achieved. You already know the goal is there. Some goal is there. You already know some solution it exists. You just have to prove the solution. Here, you have the given data is there. From the given data, you should derive a solution. Here, from a given solution, you should derive the steps which will lead to the solution. Example, so suppose you are giving the example of fever and cough. The rule is if fever is there and cough is there, then flu is there. If fever and cough, how can you write this? Uh, F and C implies flu. Okay, like that it is. But here what it is a rule. Prove that. So if fever and cough, then flu. Okay, check fever and cough. Derive fever and cough are true, then true. So okay, it does like that. So what is this? Goal is flu here. Fact is fever and cough, but here goal is flu. We already know flu. You can just write ulta from here. Then from flu, what we are getting uh, fever and cough. If this is true, then this is also true. You understood, right? That's what it means. Ding, 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 ding. Okay. Okay. So now we have this part. This part is done. Now we'll be very done. Okay. Then it is asking. This thing I had actually explained in the last video, right? So here I'll go with the define universal existence instantiation and give example for both. So here I made a notes. Okay, separately my own notes for this thing. Okay, so here somewhere that thing comes universal and instantiation and existential instance. Yeah, here we have. See here. Oh, it is. It's not actually highlighting it properly. Okay. Okay, you can see now. Nice. See, wow, it feels like blood. Okay, so you have universal instantiation and you have existential instantiation. A very simple thing it is. Okay, what he says, every instantiation of universally quantified sentence is entailed by the original sentence. Okay, what they're saying. instance of a universally quantified sentence is entailed by the original sentence. For okay, from examples you will understand. From that I can explain easily. If we have for all x, okay, suppose x is a person, okay, suppose x is some person, okay, all the persons, for all the persons, if it is a king of person, and sorry, if that person is x and greedy x, it's okay. For all any person, for every person who is king, okay, who is king, and he is also greedy, okay, oh, he is also greedy, then we can say that x, okay, like this we will derive that x is evil, okay, like that it is. So what saying, from universal quantified sentence. So from a universal quantified sentence, it is entailed by original sentence. Okay, every instantiation of universal okay, this is some instantiation of a universal quantified sentences. It is entailed by original sentences. So it is entailed by original sentence. You are understanding, right? What I meant here. Okay. Let me just highlight it properly. Okay. For all x, I think that text highlight was itself better. Okay. Let me select another highlight. Okay. Then now what I'll do? Oh, it makes no difference. Uh, so or whatever, just leave it. See, you understood, right? Just remember this example. So, King of John and Greedy of John implies evil John. King Richard and Greedy Richard implies evil Richard. Understood, right? So, what is saying? Every instance of a universally quantified sentence is entailed by original sentence. Then existential instantiation. What it says, existential instantiation, it says that for any sentence or symbol k alpha, where a alpha contains an existential quantifier, we can introduce a new constant, which is column constant, to represent the existential instantiation. For example, if we have there exist x, so from all the persons, so set of persons are there, right? So many persons are there, so many for all person, okay, so many are there, in that few person exist, okay. So now you can so on which if there is a crown and it is on their head, so we can say that, okay, we can say we can introduce a constant. So here we have, see, we don't have both x and y, don't we have specified here John, okay. So crown of x, x is a crown, and on head of x comma John, what is on head? Crown on John. So what we can say, John is a king. So what we'll do, instead of x, there exists, right? So this existential quantifier, we are converting this existential quantifier into a constant. You understood, right? That's what we are doing here. Yeah, universally instantiation and existential instantiation. In universal instantiation, what you are saying, any instance of this universally quantified sentence, it is derived from or entailed from the original sentence. Okay, it will imply for all. Both are x here also. Then whatever derived is also from this x itself. See, these two are every instantiation what we have derived here is also from this original sentence. But here what is happening? We have there exists x, so x, the existential quantifier x. So what we'll do here, it is crown of x and on head crown and comma John. So what we'll do, we'll replace this x as constant c1. So crown c1 and on head c1 comma John. So only this here, okay, this will derive this thing, that's it. The nothing else is there, okay. So this, I hope this part, okay, where it go, till here it is done, okay. Now what they are using backward and forward chaining, they are asking us to derive this, okay. I think the textbook will help us more over here. Forward chaining. So okay, see here, these are the things we need to derive. So let me just highlight this. Okay, now see here, American X. If X is an American and Y is a weapon, and X sells weapon to Z, okay, and hostile Z, Z is an hostile, then all these four things implies that, okay, criminal X, better, man, I wish there was some undo thing here. Just a second, I'll make it look more neat, okay. Then this, all these four things will imply that, okay, it is X is criminal. That's what we have to prove here, okay. So what now, how we will do this? So first, it is a crime for an American to sell weapons to hostile nations. Okay, Nono has some missiles. The sentence there exists X. So owns Nono comma X. So okay, and missile is X. So okay, so here X is a missile. So if some missiles are there which are owned by Nono. So it is transformed into definite clause by existential instantiation, introducing a new constant M1. So we saw that what is that? This topic was there, right? Which where I explained this, where it went. Here I explained that existential instantiation. So that's what it is happening here. So it will become owns Nono comma M1. So instead of writing there exists X, this thing, this thing will get hidden, and instead of X and M1 we will have owns Nono comma M1, missile is M1. All of its missiles were sold to it by Colonel West. This thing is a name, complete name. Colonel West is a name of a person. Missile X and owns Nono comma X implies sells West comma X comma Nono. So West sell to Nono this X. Okay. West sell weapons to no. We also need to know that missiles are weapons. So missile of X is equals to weapon of X. And we must know that an enemy of an America counts as hostile. So what is saying? To write that hostile, okay, okay, X is enemy to America. So then it is hostile, right? So what you are doing? X comma enemy of X comma America means X is an enemy of America. Then it implies that X is hostile. Okay, I am just saying so badly. I know I'm just confusing you all. Okay, so see here, enemy of X comma America. So here what is happening? This thing means that X is an enemy to America. If X is enemy to America, then simply we'll derive that X is a hostile. And West, who is American? Then American is West. If an American person says, well, it is criminal. If it is not an American person, it is not a criminal too. Then that the selling country, purchasing country is not the what is it, hostile to America. So the country no an enemy of America. So America. So enemy, we can simply say that no is what to say, enemy of America. So here we had X. We know that if some country X is enemy to X, then that country is hostile country. And we also know that American West. And we also derived here that West sells America weapons to no. So directly what we'll do? No is enemy to America. This thing is simply happening here. Okay. Now what we'll do? This is the algorithm. We just have to draw this diagram. Okay, now what we'll do to derive that, okay, we will having known facts. You have to write all these known facts first. Okay, write all these known facts first, draw this diagram, then you can derive that West is an American, missile is M1, no O's is missile M1, then okay, then no is America's. First what you will do, you will write criminal West. Just leave this. First what we will do, weapon X comma weapon, same how you wrote here. All these things you will have to write. If I have to highlight, okay, these things should be highlighted. All these things should be highlighted. One by one you have to write. You have from all the given facts you are deriving, and at the final thing what you are saying this. Okay. At the end, okay, what's happening? Backward chaining. Same thing how you will prove by backward chaining. Okay, in backward chaining, you will be knowing already that criminal is West. Okay. Have they derived any? Okay, they have not done. So what you'll do for criminal to be West? Okay, one what should be satisfied? For criminal to be West, it should be that first West should be American, and there should be a weapon. Okay, you can say this and this. Okay, so what they have said in the okay. First, let us read the question. As per the law, let me erase this thing. As per the law, it is a crime for an American to sell weapons to hostile nations. Country E, an enemy of America. So here they are saying country E is an enemy of America, has some missiles, and all the missiles were sold to it by Solon, who is an American citizen. Okay, so prove that Solon is, array. Prove that Solon is criminal. Okay, here what you are saying, Solon is criminal. We have to prove that. So in backwards chain, what do Solon is criminal. Then how I will be deriving? Okay, let me just draw here. If Solon is criminal, then I'll say Solon should be America. So okay, not like this. So I'll draw American of S, and okay, Solon is American. Then what I have to also prove that if Solon sells weapon to any hostile country, then only it will be like okay, there sells, okay, then only hostile is, okay, then only we will say that Solon is criminal. So what you are doing here, so we are saying Solon is American, then there is some weapon Y, so Solon should sell this weapon Y to some country Z, and we are also saying that okay, from this, now this is over, weapon is Y, then after what I'll do, okay, I'll just explain it more properly now so that you have to understand it. Okay, first what I'm doing, I'll highlight it normally. Let me highlight it blue normally. So first I'm deriving this. After deriving this, then what I'm saying, weapon, first I'll write these two together, then I'll write, let me use another color, then I'll write this two, then array, I did not change the color. Then what I'll do, I'll write these two together. Oh my god. Okay, wait, where is this yellow one? I'll just take. Understood. Then what I'll do, again let me take yellow itself, then I have to array, write these two together. Okay, once I write these two together, then what will become, we'll derive that America West has weapon. Okay, then what I'll do, then I'll go with this, like this. I, shit man, was so psychic. Then I'll go like this. If I comes here, if I have to say, okay, so I derived that Solon is American, Solon has some weapon, okay, that weapon is nothing but missile Y. So we are saying that missile Y is M1. So we read what I read, Solon American, okay, I just made a draw here, American Solon and weapon M1. Then what I'll write, again I'll write, for this to be true, okay, for this thing, if Solon has to be American, then I have to say that it should be proved that it sells, okay, sells, this Solon sells missile to some country Z. Okay, now what I'm doing, okay, owns nano nono comma M1, and here missile comma M1 is there. So for this Z, okay, now what in question they have given, country E, right? So a country E should be an enemy of America. So the hostile country here we are deriving is, okay, instead of no, just write E type thing. Okay, then what you're saying, missile M1 and owns nono comma M1. So in forward chaining, what we said, if missile M1 is there and no owns on nono comma M1, then which means that West has sold missile to nono. But here what we're doing, we already know that someone has sold. Okay, he has already sold this to Z. So now to prove that this Z is no, what is that? No. In actual, from the actual question, Z is what to say. Country E, then I have to write missile M1 owns country E comma M1. I will do it like that. Then what I will do? So hostile. So now I have to prove that E is hostile to America. Okay, hostile of E. So E is an hostile. Then what I'll do? Enemy E comma America. That is all right. Okay, you understood a very simple thing. So you have to write the same thing ulta. Let me just go up. I know I have messed it up. I can explain it later properly after if you have seen this thing. So see here, one by one from the end I will be writing. Okay, first write this. If you learn this is enough. If you are writing from this side, okay, you have to write like this for forward chaining, and you have to write like this for backward chaining, and keep on proving one by one like this. Understood, right? Keep on proving one by one like this. That's all you have to know for forward and backward chaining. Nothing else is there. Then explain unification and subsumption lattice with example. Unification I can explain here. So unification is nothing but a process that finds substitution to make different logical expressions look identical. Okay, so it's nothing but you are giving some substitution type thing. Instead of writing that whole thing, a plus b, a into b into c is there. So now what you will do, you will write a into b as d. So you will have only d into c. Okay, given two expression a and b, we want to find a substitution such that a in theta is equals to b theta. Example, suppose we have king of x and greedy of x matching king of John and greedy of y. Okay, now see here, this thing first. Okay, let me use highlight here. Now I won't miss it. Okay, like that. Okay, king and greedy is matching here. You can see king and greedy is matching. Okay, which else color will look good? Let me try green one. No, okay, green is not helpful. Let me use red. Okay, wow, man, nothing is visible. Erase. Okay, now it's nice. Instead of x we have John, and instead of again another x we have y. So here I can now derive that x is equals to John, and x is also is equals to y. Then I can simply say that John is equals to y. Understood, right? Substitution theta is equals to x comma John, y comma John works. So now I can say theta unify a comma b is equals to theta if a theta is equals to b theta, which means x is equals to John, then y is equals to John. Okay, or else if is equals to John and x is equals to y, then what to say, a is equals to b, you can say that unify a comma b. So both are same. Unify a comma b means simple, you are making a and b both are equal. Simple, you can understand, right? Here theta, okay, is equals to theta. Okay, I'll explain once again. It's very simple. So what's happening, theta is x, suppose theta is x. So, okay, this theta and this theta, if x is equals to John, see here, and x is equals to y, then what I'll do, I'll unify John and y. I'll unify John and y, which means John and y are equal. Understood? That's what unification means. Unification is essential for lifted inference rules and algorithm. Okay. Let me see in this if I have something about okay, submission lattice. Same thing is written here. No need to submission lattice. Subsumption lattice is a hierarchical structure that represents the relations between different concepts of sets. Okay, instead of subsumption lattice, you can simply remember it as subset. Okay, subset. Don't get confused. Simple, it is like subset with one concept or set. Subsums another if it includes all the instances of another. So consider the following set. Set A is animal, set B is mammal, and set C is dog. Okay. So we know that all animals are not mammals, but all mammals are animals. You can say that, right? What I'm saying, all mammals are animals, and all mammals cannot be dogs, but all dogs can be mammals. Okay, because we have a variety of mammals, so many cat, dog, and humans. But all mammals are not dogs, but all dogs can be mammals. So I can simply write, right, set A subsum set B, which means B is a subset of A. So if I have to write, instead of writing, wait, I'll draw here. So B is a subset of A. Okay. So if I have to write it in ulta reverse way, so what I'll say, A subsums B. Understood? Similarly, B subsums Set C. Just write all mammals are animals, all dogs are mammals. Understood? That's what it is here. Then what have they asked? Write a short note on first order logic can be applied in Wumpus world. Okay. So how first order logic can be applied in Wumpus? So first order logic FOL can be applied in the Wumpus world to represent and represent and reason about the environment more expressively than propositional logic. Example: facts. Wumpus x comma y. There is a Wumpus at location x comma y. Simple. Pit x comma y. So these are the facts. If there is Wumpus at x comma y, then there, if Wumpus of x comma y means there is a Wumpus at location x comma y. Pit x comma y means there is a pit in that location x comma y. Breeze x comma y means there is a breeze at location x comma y. So what you're doing, for all x comma y, pit of x comma y implies breeze x plus 1 comma y. What it means that suppose I'll just take here, this is 1 comma 1, 1 comma 2, 1 comma 3. Okay, so what it's saying, for all the 4 places. Okay, okay, then better let me do like this. Okay, I'll draw here, it is nice. Okay, I need one more row. I'm just explaining, don't take thing like this. So if pit is here, this, suppose x comma y is this place. So what is this place? If I came 1 2 3, is 1 2 3 4. Okay, so this is 2 comma 2, right? If pit is in 2 comma 2, so here what is having, the pit 2 comma 2 implies it is, okay, here did not come. Right arrow means implies there is breeze in x plus 1 comma y. So 2 plus 1 is what? 3 comma 2. Here it is 1 breeze is there, or it is or, okay, or breeze in x minus 1 comma y, or breeze is here. Then or x comma y plus 1, so 2 comma 3 here. It can be either here or it can be either here. Okay, that's what it is saying. That's it. These all things it is writing in this one. Okay, b of what is that, 2 comma 3, or b of like that same 1 comma 3, like that we will be writing, or b of 2 comma 3, or b of 2 comma 1. Understood? Like that. The rule states that if there is a pit at x comma y, then there is a breeze in the adjacent cells. Understood? That's what using FO logic, the agent can infer new knowledge and make decisions based on the logical relationships between objects and their properties in the Wumpus world. Okay, that's it. Nice. You understood, right? Reasons and failures of first order logic. I think this comes under. Okay, now write appropriate quantifiers for all the following. For the following. So it is asking us to write the what is that quantifier. Some students read well. Okay, you can say that a universal thing x means students, set of universal set of x where x is student. Okay, you can say that there exists x comma read well of x. Okay, that's it. Then some students like some books. So you can say that let B be a set of books. So now here I'm defining B as set of books. Okay, so now what I'll do? Sorry, there exists X, there exists B. Okay, likes B comma sorry, X comma B. Okay, like this. Then some students like all book. There exists X for all B, same likes X comma B. All student likes some book, then simply it will change. For all X there exists B, just write this statement. Okay, then last, all students likes no book. Okay, no books. So what we'll do, for all X, for all B, what we'll write, likes X comma negation B. So if for all B means all B, negation B means no books. Understood, right? Very simple it was. I hope you understood. Then extend the concept of resolution in first order logic with appropriate procedure. So resolution in first order logic. So have I explained resolution in first order logic here? Okay, which question was I? That was different question actually. Sample say, okay, I did not. Okay, let us see here. In this, if this guy had explained. Forward, backward, forward. explain unification. I have explained this. Done. Then write appropriate. Okay, this I did. Okay, you can see here. For all x, s of x implies for all y, b of y implies. Hey, what man? This guy has written so confusing. Che, you don't have to write the so. Okay, like this and all. Okay, what I have shown is nice. S of x and r of x. Okay, what is that? Some student read well. Okay, so it's saying it's I directly to read well of x. So what is saying? There exists x. So student of x, some student, and read well of x. So this is also simple, right? You can understand here. So instead of writing also, there exists some student. Array, etc. There exists some student reads well. Both are satisfying here. Then for second question, some student like some book. So what we are saying, some student, okay, there exists x, there exists y. So what we'll do, some student like books. Okay, student and books and likes the x comma y. So it's writing like this. So what it means, some students and some books and imply. Okay, it's not, I don't feel this completely correct. Okay, some students like some book, right? Student of x, okay, and and book of y implies likes uh, x comma y. This is more likely good. No, instead of and, this should be this, right? And likes. Okay, that is also fine. So you are saying some books are there, some students are there, some books are there, and x likes some books, like that it is. That is also fine. There exist. So then here some students like all books. So here there exists x. Here outside only you can write that there exists y. S of x and b of y implies. So you didn't have to change so much here. You can have here directly it's saying, right, some student like all books. So some x, there is x, there exists for all y. S of x and what s of y, b of y implies L of x comma y. You can actually create your own thing also. Okay, then all students like some book. For all x, there exists y. Okay, s of x implies there exists y, b of y, and likes x comma y. So this guy has done so much complicated. You can anyhow, I have explained you here, right? You can either go like this, how I have explained, likes b comma y. So okay, x likes b. So this is also very simple and easy thing. You don't have to go so much. Okay, anyhow, we came for resolution first order logic. Resolution first order logic is a rule of inference used for automated theorem proving if it is a resolution based method, meaning it proves the unsatisfiability of a set of clause by deriving a contradiction. See, so many things is there. Okay, just see. Okay, I think this is what is the theory part. I'll explain the what's the left out part. So only these many questions. Okay, I'll stop this video for now. I'll in the next video I'll just get the proper notes and then I'll explain those remaining topics for you properly. Okay, thanks. Bye bye. Bye bye.
Can I please ask you to subscribe? That's all we want, man. Just press subscribe.